Hey, hi everyone, this is Vivek, and in this particular video, we're gonna solve all the problems of the ICPC India 2021 preliminary online round that happened yesterday. Okay, so this was a really great round, a 2.5 hours kind of round where we had like around 7 problems. Six, like the highest team kind of solved six, which I think is like reasonable. Solving all seven in 2.5 hours, like coding them from scratch, would be very difficult. So we're going to go through all the problems and we're going to discuss the ideas that were there for these problems, and like whichever problem you thought would be like the one that you couldn't really solve, you can get into that particular problem and understand the idea, right? So let's get into the problems and let's start from the first one. We're going to go in the increasing order of difficulty. So first we'll start with cakewalk, then easy, medium, then medium problems, then one of these, like the hardest problem was over here. So let's start with the first one, which is cakewalk. Then we're going to get into simple, okay? Then we're gonna get into, let's say, easy, medium, easy, then easy, medium, then medium, and then medium hard, right? So we didn't really had any hard problem in this one, though I think medium hard was one of the hard problems. But still, if you know what auxiliary tree is, you could have solved this problem fairly simply. I mean, like if you have solved auxiliary tree or harder problems of auxiliary tree before, I think you should be able to recognize it and then solve it. But doing it in a 2.5 hour contest is very difficult, and that reasonably tells us why like we had only 6 submissions in this contest. So let's start with the first problem, which are fairly simple to start with. In the first problem, what we are given is that you are given n+1 stones, 1a, a square, a cube, up till a to the power n. Now, in this particular problem, you have to find out the middlemost like stone. What is the number written in that? Okay. So let's say if you have n equal to 2, so you have a to the power 0, a to the power 1, a to the power 2. Okay, and you have to find a to the power 1. So it's very simple. In the problem, it's given that you have to find out 1, a to the power 1, a to the power 2, up till a to the power n. In this particular sequence, you have to find out which is the middlemost element. So it is always given that n is even, which means finding the middlemost element becomes very simple. We can just do n by 2 and that will give us the middlemost element. Like if you have 1, a1, a2, the middlemost is 2 by 1, which is 1, right? So n by 2 will give you the middlemost element, and you have to simply find out a to the power n by 2 with the given modulo in the problem. So that's all the question is. Over here you can see the problem. So we have to find out modulo 10 to the power 9 plus 7. Okay, yeah, so we have to find out with modulo 10 to the power 9 plus 7. So it's just a direct question of finding exponentiation. So find out a to the power n by 2 mod 10 to the power 9 plus 7. This is a direct problem of binary exponentiation, where you just use like this can be solved in order log n. Okay, and that is what I think was expected in this problem. Like you can just solve it with a direct exponentiation formula. You can look up the term like technique of binary exponentiation if you're absolutely new and you don't even know that. You can search that particular thing and you can solve this in order log n for every test case, and the rest is very simple, right? One more thing which is there in this particular problem is that a could be negative. Exponentiation also handles that, but make sure that you handle the modulo correctly. I mean, when things are like negative, you need to make sure that the number that you get from the exponentiation can be negative as well. So make sure that you make it positive at the end. That's the only thing that was required to be done in this particular problem. Fairly straightforward, just two simple things. Maybe like having negative numbers is one thing which might kind of throw you off the boat, like if you can do that or not, and like doing modulo property. These are the two like small caveats where you could have got a wrong answer. So that's the first problem. Let's move into the second problem now. So the second problem was this operations on binary string problem, where you are given, let's say, a string s, n and x coins, and you can do the following any number of times. You can choose any substring of length k and flip all of its bit in a chosen substring, right? The cost of this operation is 2 into k plus 1. Now you have to find the maximum possible number of ones in the binary string that you can do after like using at most x coins. Like there is a budget given to you, and flipping k positions, k length substrings cost you 2k plus 1 total cost. Okay, it is allowed to do 0 operations as well. So you can just throw like not do anything as well. If all of them are 1, you don't really want to do any operation as well, right? So how do we solve this? We are given a bigger, like the constraints are pretty big. Like we are given 10 to the power 5 or 2 10 to the power 5 length strings. Since the sum is up till that much, we could ideally try and solve this in n or n log n kind of in complexity. And the x is given too large, but I don't think we're going to need that much anytime soon. So let's kind of see what is the maximum like thing that might be required. So if you have, let's say, a bunch of zeros followed by bunch of ones, followed by bunch of zeros, followed by bunch of one, followed by bunch of zeros, something like this might be the string, right? Any string which is 0 1 1 0 0 0 1 0 1 1 1 1 0, something like this, can be compressed into x number of zeros followed by y number of ones, followed by z number of zeros, followed by a number of ones, b, something like this. We can compress the things together, that there are x consecutive zeros followed by y consecutive ones, and so on. So now in this case, what we can try and see that if we just convert this x like a single zero over here, like a continuous piece of zero, we're gonna need a 2x plus 1 total amount of cost. Okay, and if we convert this one, we're gonna need, let's say, 2z plus 1. Okay, so these are the two independent individual costs that we are going to incur if we convert these two zeros independently. Now, one like small kind of an operation that might be possible is, what if we try to span across some ones, flip it, and then flip that one back to zeros? I mean, that is something which we might try. Okay, so maybe this is some kind of an operation that we might try and do, that we flip this much and then flip this much. Okay, maybe this might lead to an optimal solution if possible. I don't know, maybe. So let's try to see. So in this case, we were converting everything into like ones in this much of portion. Okay, now if we use all of this particular part, maybe the total amount of cost would be required is 2x plus 2y plus 2z, okay, plus 1. That would be the total cost. And to convert this back again, you're going to need plus 2y plus 1, right? This is the cost to convert this much of the string, because there are y characters, and this is x plus y plus z characters, so this much. Now you can obviously see that if you convert this whole thing over here, if you go across a particular one, we have to convert that one back to a 0, right? And you're obviously not getting any benefit over here, even if y is equal to 1, right? Even if y is equal to 1. Forget about, let's say, this one, okay? Even if y is equal to 1, we are kind of incurring 2x plus 2z plus 3 cost, okay? Plus 3 cost. And we are still getting, like, these are converting to zeros, these are converting zeros, but we are getting more zeros in the process, because the one which is in between is getting converted to 0. So it is higher cost with a lower result of zeros, with a lower number of ones, right? So it is never optimal to cross across any one in the whole operation. So we never take a substring which is going to cross across ones. That's the main observation. Apart from that, now if you know that that is true, then if you have bunch of zeros with length x, then some ones, then bunch of zeros with length y, then some ones, then bunch of zeros with some z, right? We know that we are never going to go across these ones. So all the operations that are going to happen is going to be in this much portions itself. Okay. Now, it might like directly intuitively kind of come to your mind that we might try to take all of it, with some of them, all of it. Which one should we take? So if you see the cost, 2x plus 1 is the cost, right? For an x length. Okay. So if you take a bit, like for every character, you're paying 2 cost, plus just to convert a continuous chunk, you're paying a 1 cost. Okay. Any number of characters that you convert in that one operation, it's going to cost you 2, plus 1 conversion costs you 1. Okay. So if you start converting something, you would love to get as many zeros converted as possible, right? So which tells us that we can try and use a greedy strategy that, okay, pick the one that has the largest, like pick the one that has the highest number of zeros, x, y, out of x, y, z, and convert that range of zeros into this. So let's take an example. Let's see, we have 3 different ranges. This contains 8, this contains, let's say, 3, this contains 5, this contains 1, okay? Something like this. And let's say we happen to have, let's say, 15, total number of things that we have is 15. Total x is equal to 50, like we can convert, I'm gonna just give you a quick number. So the first, I'm gonna give you the number right over here, like what could be the budget, but let's say we would try to take like all of these 8 first, because if you start over here, pay 1 cost to start, okay? If you pay 1 cost to start, you would be able to convert as many zeros as possible in that same run. So that 1 cost would be used as much as possible, right? Anyways, every character takes 2 costs to kind of convert. So get this much converted greedily, then try to get this much converted greedily, then try to get this much converted. So to convert this, you will need 8 into 2, 17 cost. To convert this, you will need 5 into 2, let's say 5 into 2 would be 11, 5 into 2 plus 1 would be 11. This would need you 3 into let's say 2, 7, okay? This is gonna need you 3. So these are the costs needed to convert each of these segments, right? Now, what if you have just, let's say, let's think about having 34. Okay, 34 as the given x value. What if 34 is the given x value? Now in that case, what we can kind of look into is, if you have 34 like x value, we can convert this much. So you will pay 17 cost and all these 8s would get added as a 1. Next you will pay 11 cost and you would be left with 28, so you will be left with 6. Okay, so you would be done with this much also. Like these all would be converted to ones as well. These all zeros would be converted to ones as well. You would be left with these zeros over here. Okay, there are 3 zeros over here. Now you have 6 left. To convert this you need 7. So you can definitely not convert all of them, but still you can convert some, right? You can start over here. Okay, you can start by paying a 1 cost, and then for every character you're going to need 2 cost. So so you are left with 5. How many characters can you convert? 5 by 2 equal to 2. So you can convert 2 characters. So from out of these 3 characters you will take 2 characters, right? So greedily take as big chunks as possible. Okay, once you cannot take the full chunk, try to take as much of the zeros as possible from that by paying 1 cost to start, and then take 2 for each character. So just divide by the rest left by 2, and then you get the number of zeros. So that is how you can find out the number of zeros there. So the question would like resolve down into finding the continuous sections of zeros. That is the first part to do. Next is put them in priority queue and find the biggest chunks first, take them out and then use them to convert from this one, okay, by their full cost. And then if you cannot do it for a particular segment, see if you have at least 3 characters, 3 like cost left, then in that case, like you can subtract 1 from it to start, and then for every character you will pay 2 costs. So whatever is left by 2 is the number of character out of the next one left you can convert. If there is no 0 left, then you stop the process then and there and say that like you have converted everything, right? So that's the whole solution for this particular problem. You can solve this problem in O of n log n. That should be enough for this particular problem, okay? And since like sum of n is given to be up till a given number across test cases, you will not need more. I mean, it is not t into n. Don't get confused with that, okay? So that's almost all for this particular problem. Let's move into the next problem, okay? So the next problem that we're going to take is red and blue. This is a very standard problem. I felt this is one of those classical problems that kind of is disguised in like a different setup and is been asked. So the question is like you have a string s and you have to color everything into red. The thing that you can do is you can take a particular like color and set it to all the colors in the range I plus 1 to I plus t. And we need to make everything red, find the minimum number of like spills that you have to do in this case, right? So I'm going to assume that you have read the problem. Now this is one of those problems where I feel like if you have solved similar problems, there is a problem called dominoes, which is also very similar with this one, where you have to like twist a domino forward and then it is going to make everything fall in forward as well, something like that. So this is also in the similar lines. Just that I think there was one like confusion that I thought that was not clear maybe, is that if you color some blue into red, then can that new red be used to fill things in the forward as well? But I'm going to assume that we can do that and solve it. So in this case, we are given the string over here. We can spill the red to the next blues and stuff. So what we do is we go forward and try to set things into like red, and we have to do minimum such moves, right? And the constraints for this is up to 10 to the power 6. So we have to do something sort of linear or n log n maybe. Okay, so let's try to do this one. Let's say there is a red. So first of all, what we try to think about is till where can we convert things to red? This is what we want to maintain, okay? So let's say there is a red, red, blue, 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 red, blue, blue, red, blue, something like this, okay? And for each of the elements, you are also given a D array, which says, let's say 2, let's say 1, let's say 0, let's say 5, let's say 3, let's say 2, let's say 1, let's say 0, okay? Let's say 1, let's say 0, okay? So over here, we are given different segments and we are starting with like the first element. We want to convert each element to a blue. So obviously the first element influences the next things. So if you can decide what you do at the first element, then like things are set for the next things, right? Okay, now we can also think it this way, that these 2's that are given, it's like we can fill this much range. This says that we can fill this much range. This says that we can fill only this much, like we cannot change anything. This says that we can fill like, let's say the next 5 elements like over here. This can fill the next 3 elements over here. This can fill the next 2 elements. This can fill the next 1 element, right? Something like this. So this is what is given. inclusive of that, I mean to say like 5 inclusive, like 3 inclusive of that, it's already like red, then only it can spill things up. Okay. So over here, like what we can kind of do is we can go from the forward and try to see when do you need something to be spilled onto this particular element. Okay. So this is a red, right? We don't need to do anything. But if you spill this red, you can potentially get to 2, like index 2, right? So what we will do is we will maintain 2 variable. What is like one is last covered, okay, which is till which particular point have you last made everything red, okay, last covered. The next thing that we're gonna maintain is potential, like where can you make or possible to cover with one flow, with one spill operation. Okay. So last we have covered, so let's say these are indexes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So last we have covered till, let's say, -1. Okay. We have covered till -1. We have, let's say before that everything is red. Now, and we can possibly maybe cover till also -1 only. We cannot do anything better than that as of now. Now, if the first element, like we are now going to go through I, so for I equal to, let's say 0 to n-1, okay, n-1, that is what we're going to do. And for a particular index, what we will do is we will check, is that one of the elements in the last covered things. So if the current element is already converted to red, then we are good to go. We don't need to spill anything forward. But if it is not, then we have to check if it is inside the possible covering thing. Like maybe with one spill, can we cover this? If yes, then we will spill that thing and spill it to the most distant. Okay. So possible cover is going to maintain the one segment that spills to the rightmost element. So what we're kind of doing over here is, if you are at a particular blue, and let's say there is a segment which fills till this much, and there is a segment that fills till this much, obviously you will pick the one that fills even further, right? Because everything in that case would get covered. So we will always maintain is that with one more spill, what is the farthest that we can try and fill? Okay. So we will maintain last covered, which is till how much we have already covered with the spills that we have done. What is the farthest rightmost cover that we can make with one more spill? Okay, this is what we maintain. And then we go through the elements one by one. Okay. So if we go through elements one by one, if let's say the current element is B, okay, if the current element is B, okay, if I is equal to, let's say B, in that case, it's a blue, right? And we need to make sure that this gets covered. So there are two cases that can happen. What if I is less than equal to last covered? Okay. What if it is already covered? Then there is no problem. It is already covered by the things that we have spilled. So this blue is already covered by the spills operation that we have done before. Okay. What if it is not spilled as of now? In that case, there is another case which can happen is I is less than equal to possible spill. Okay. Possible cover. So that if you spill one more thing, maybe that we can get it covered. Okay. The last thing that can happen is that I is bigger than possible cover. Okay. So in this case, it's already fine. No change, no extra cost. Okay. So you will get +0. You don't get any extra cost. If it is less than equal to possible cover, it is not covered and it is, so you are at a particular B, let's say over here. Okay. And it is not covered as of now. So you have to spill one of the previous reds to make sure that this is now covered. So you will spill the one that goes the farthest and get this converted. So what will we do is that we will spill the farthest possible coverage. So what we will do in this case is we will make last covered equal to possible cover. Okay. Like we will spill the one that was doing to the farthest. And we will like do an answer plus. That will make sure that we have a final answer incremented because this was spilled to the forward direction. Okay. And if it is not possible, then the answer is always -1. If it cannot be done with any of the spills previously, so think about this particular case. Over here, we have by default -1 for both the like fixed and possible. Okay. Now when you get this red, you can possibly fill to the index plus D. So till to index 2. So possible is up till index 2, but currently we have filled only till -1 because it's a red. I don't need to spill it further, right? Unless it's required. The next one is red over here. It can spill till, let's say, index 1 over here. So D is 1. So 1 plus 1, 2. But so possible remains the same. Okay. Because this can spill till 1, 2 only. and then this is -1 only. Now you come to a blue over here. It's a blue, right? And it is not in the fixed, already filled range. So you have to spill one of the previous reds to make sure that this happens. So now the fixed ones will become 2, and you incurred a +1 cost over here. Okay, you incurred a +1 cost over here, just to kind of get it done over here. +1 cost over here, and in this case you're gonna have still the possible, like if you made this red, now if you try to spill this, you can still go to only 2. Now there is a blue over here which is at index 3, but even the farthest that you have filled till now is not covered, is not covering this index, and you can not even cover them with the previous thing. So it is not possible to convert this one. Whereas if we, let's say, convert some of these values, just let's go back a bit of the elements and change some of the values over here. If we, let's say, make this one 3. Okay. So what happens in this case? We still have like filled till -1, but we have possibility till now index 2. Now this one is 3. So we have filled till -1. Since this is red, we will not change anything. But if this spills, okay, we can go till 0, like 2, 3, 4. These 3 will be filled. So 1 plus 3, we can go till 4. So we will update the possible coverage that we can do. So now if we spill this red one, it can cover till this much. But if we spill this one, it will cover just these 2 elements. So now going forward, if for a particular blue, if we have to spill an element, we will definitely spill this one, right? The farthest that we can go, because that will be the better choice. And this is a greedy algorithm in this case. So this is what we do for this particular problem. This is the whole algorithm. I mean, over here, we, like, after we have converted these 3 things, if it is a blue, we will process this, and we will do simply possible cover max with, let's say, the farthest that you can do. So I plus d of I. Okay, you can go to this particular index. So I plus d of I is the new possible coverage using this element too. And whenever it will be required, it will be covered over here. So that's the whole idea that you will use for this particular problem. This is the full idea that you can use for this one. If it's a blue, see if it's already covered, fine. No need to change, just update the possible color. This happens irrespective of if you go into this condition or not. If it is not covered yet, you have to get it covered. So answer is going to increase, and whichever one was trying to fill to the farthest, you will use that. So now the last cover will become to the farthest that you can fill with one more spill. And if it is not possible with even possibilities of the previous spills, then you can never do this. For an example, if the first element is blue, that's never possible, right? So that's how we solve this particular problem. This is all going to take an order n process. This is an O of n solution for this particular problem. This is a classical problem, but a very nice problem. Like if you have not solved something before, I think you might face in some trouble in coding this clearly, right? So that's almost all the solution for this particular one. I hope you could have solved this one. Now, if you are like liking this particular video, and if you like enjoy more such streams on solving great interesting problems, make sure that you like and subscribe to the channel. We're going to move to the next problem next. Okay, so the next problem that we're going to take is Lexis, right? Even though I felt that the beautiful array was a problem that was like easier than Lexis, but I think we saw more submissions on Lexis. So this is one that I will take first. For this one, what we are given is that we have to choose substrings out of the strings. Okay, so we have to choose substrings out of the strings. The first thing that we have to do, ensure, is that every string that you take, substring that you take, they are increasing in its lexicographical order, number 1. Number 2 is that the sum of the length of the substrings, there is an a cost, a of the length. That value would be added if you choose a string of length x. Okay, a of x would be added to the answer. So you want to make the maximum possible score by taking substrings that first of all don't overlap. Next, they are in lexicographical order. Okay, from left to right, and whatever best we can do, that is what we need to find. So just to understand, let's say if you have something like A, B, C, A, D, B, A, something like this maybe. So one possible solution is that, like, if you take this and then you take this, so you get A of 2 plus A of 2, the length of the 2 strings that you take. Okay, and like since like the BC comes before DB in lexicographical order, it's fine. You can even do this, that will give you A of 1. Okay, because A comes before lexicographical order in this one, right? So you need to choose non-overlapping substrings from the whole string such that their sum of lengths cost is maximum. Okay, note that this is not feasible if you choose this and this. So obviously they are not overlapping, but AD comes after BC, but it's lexicographically smaller than BC. So this is not feasible. Okay, you cannot take these two things. Even this and this is not feasible because like BA is less than BC in its lexicographical ordering. So, but it's coming after. So you have to keep increasing in lexicographical ordering and still make sure that you are getting the best solution possible. Okay. Okay, so the constraints for this problem was up till 500, which made it a bit more simpler. I mean, this could have been made a bit harder, but I guess it was good that it was up till 500 so that you could directly understand this might be a DP problem, right? This is one of DP problems that could have been, that was there in this particular set. So what we can kind of think about is how do you handle the two conditions given to you? Number one, no overlap, okay? Number two, okay, what do you do with lexicographically ordering? These are two constraints that needs to be handled in the like the sequence of strings that we are substrings that we are forming. No overlap between them in the ranges and lexicographical ordering. Okay, so you need to have practiced some similar DP problem before maybe to kind of get an intuition. But how do you handle no overlap? So for every index you could take this much, this much, this much, and so on, right? So in general, for such problems, what we can do is maybe, or even like, let's say for every endpoint, like ending at this, you could take this string, right? This string, this string, this string, this string, so on, right? So what we will do is, for a particular endpoint, we will try to find out what is the best you could get till this much. Okay, this is what we will try to find. So this is one of the form tools. If you don't know what forms are, I've covered that in the DP workshop on the channel. You can check that out. But form 2 is essentially nothing but ending at this particular index. So what is the best solution that ends at this particular index is what we will keep in DP. DP of index, okay, is going to be equal to best subsequence of substrings. So in this case, we have to find subsequence of substrings, right? Substrings ending at index some I, okay? But there is one small problem in this case. This handles the overlap case really well. Why? Because let's say over here, you have to find out DP of, let's say, some I, DP of certain index I. So what you will do is, DP of some index I, what you will do is you will simply go ahead and let's say this is the index I, okay? You will find out, okay, maybe the last string that was taken was this, or maybe this, or maybe this, or maybe this, or things like that, right? This is what you can try and iterate on. But the problem with that is, like, let's say you take this one. So you know what length you took. So let's say you take a length L over here. So in that case, you will get a of length cost plus you will have to solve for DP of I minus L. Like from this much, what is the best you can do? But there is one more constraint, which is the string that you take now before this string over here from this side has to be lexicographically smaller than this particular string, this particular substring that you're taking right now. Now that is another constraint which is not really modeled well in this particular DP over here, right? That is not really well modeled in this particular DP. So how can we handle that? That is the main caveat of this particular problem. What makes this problem a bit more difficult, a medium problem to be precise. How do you handle this? Lexicographical ordering, because no overlap is fine. This is something which is very standard to handle in DP for ranges. When you have range thing, you like take the range and then you go to the next thing. Even like yesterday itself, like I made a stream where I talked about this projects problem from CACS that has a similar kind of an idea, right? Weighted scheduling kind of problem. But how do you handle this lexicographical ordering is the next main thing that is required in this problem. So we will learn this thing next, okay? So first of all, to understand lexicographical ordering, we need to understand how the substrings are ordered. First question to you. How many substrings exist in a particular string? So we'll next go into lexicographical ordering. Okay. Lex ordering. First question. How many substrings does a string have? Okay. Obviously that is going to be order n square. To be precise, it would be n plus 1 choose 2, right? It would be n into n plus 1 by 2. That many strings would be existing. That many substrings are possible. Okay. Order n square number of strings. Now, if there are n square number of strings, if we try to order them, if we try to order which string happens to be coming first and second and so on. So let's say you have A, B, A, okay? So the order would be first A, then let's say this AB, right? Then ABA, then just B, then BA and things like this. So this would be the lexicographical ordering of all the substrings, right? This, you take the substrings that are feasible and just find out their sorted order. Okay, lexicographical ordering. Now this is a very, very classical problem, which is like generally is used to find out, let's say, for every prefix, what is the order. Like if you want to find this lexicographical ordering, suffix structures are generally which is used, but for this problem you are given n as up till 500. So we can even do a O of n cube computation to solve this problem. So we will not get into that much of complexities for today. Okay. Instead, what we will just need over here is we need to find out this order that, let's say, from a segment L to R. Okay, if you have to take a segment from L to R of the original string, let's say there is this string equal to something over here. If you take a portion from L to R, okay, and if you take a portion from, let's say, A to some X to Y, okay, is this substring bigger or smaller than this particular substring is what we need to find out. Let's say this is what we are interested in. Okay, how do we do this? So to find this out, there is a very simple way that is generally devised, which is to compare two strings. Okay, two strings A and let's say X and Y. If what is the lexicographical ordering? What we find out is that first of all there would be some common characters, and then there would be some character which is different. Okay, so that is the decider one. So what we do is we have to find out where the first different character happens in both the strings from the start. If nothing happens, the one with the smaller length is lesser. But this is what we kind of find out, where is the first different characters. The way to find it out is also that if you maintain what is the common prefix between the two strings. So what we compute for this kind of a string is LCP of I and J. This is what we will maintain for the original string, this S string over here, okay, which will tell me what is the length of the longest common prefix of S of I till end and S of J till end. Between these two strings, what is the longest common prefix? It will tell me this. Just for an example, let's try to see. Okay, let's say A, B, D, A, C, or B, D, C is over here. Okay, and let's say we want to find out for I equal to 0 and J equal to 3. Okay, so what is the longest common prefix between these two strings? So if you consider like this whole string over here and this whole string over here, A common, B common, D common, then A and C, they are different. So 3 length is common. So the way we will write this is LCP of I comma J, in this case would be equal to 3. What is the longest common prefix between the two starting points of these things? Okay, the way we can compute this is like this is an O of n square matrix, right? For every pair of indexes we are finding this out. The way we can compute this is very simply using standard computations of one step forward. So LCP of I comma J is going to be equal to 0 if I, like S of I is not equal to S of J, okay, or else it's going to be equal to 1 plus LCP of I comma, sorry, not I plus 1 comma J plus 1. This is else case. If it is not same, then there will be no common thing, or else if the first character is common, 1, the first plus common character, plus what is the common thing from this to this? You can see that this is nothing but 2 as well. So you will find this as 2 and this will be plus 1, which is going to be equal to giving you the value 3 over here. Okay, so in O of n square you can find out, so this is again like a DP in itself, but in O of n square you can find out the longest common prefix of every two index that you need. Okay, because every I comma J depends upon I plus 1 comma J plus 1. That's how it works. So very, very simply. Okay, so this is an O of n square computation to calculate the LCP of two different indices. Okay, now what we will do is we will try to go through all different like substrings that are there, and we will go ahead and sort them up. Okay, we will go ahead and sort them up. So what are the different strings? Let's say S is equal to A, B, C, A, something like this. Okay, so what are the different strings that are possible? The way we can represent strings is by strings, or we can go ahead and maintain them with like pairs of the range that they like kind of contain in the original string. Sorry, 0 to 2. We will use 0 indexing, let's say. So this is something we can maintain, that 0 to 2 string, 0 to 1 string, 1 to 3 string, something like this. These are all different substrings of, let's say, length 3, length 2, length 1, sorry, length 3, right? So these are different substrings that are there. How many substrings would be there? O of n square. Okay. Now what we can do is we can sort these particular strings over here, these pairs over here. Okay. So we can sort this particular like n square element over here. How can we sort? There are multiple different ideas that you can use. Personally, what I would use in this case would be to go forward and try to segregate out the ones which, so radix sort is the general thing that you can use. What I would do in this case would be to use a general sort maybe with a comparator which is working in order 1. Okay, so there are n square elements, so it will take n square log n to sort these things, provided that you can compare two different strings. Okay, so you can use a normal sort with a comparator to compare two different pairs. A pair signifies a substring. To compare two different substrings which is bigger or which is lexicographically bigger, you can simply use this LCP array. How? So let's say there is an L to R given to you and a to B. Okay, what we will do is we will find out the LCP of L and A. Okay, L and A, these two positions. Now you will find out this to be, let's say, some X. So L plus X is the first character that differs, and A plus X is the first character in this string which differs. Compare these two characters. Make sure that you check that they are not going behind, like out of the string. In that case, just treat it with a dollar maybe, or let's say treat it as if like it is always smaller, like the one which is smaller length is smaller if that is happening. But compare these two characters and you will know immediately that which of them is smaller. Okay, so there are n square elements over here. You can sort them in O of n square log n square, but that is log n only, because the comparison is now being done in O of 1, provided that you have created this LCP array. Okay, so comparisons can be done in O of 1. So now you have different substrings that are available with you that you can use for such a process. Okay, you have A to, like, all the different substrings of this, let's say A. So in this case, let's go up, let's go use this simple string over here. For this one, you will have this as 1 to 1, then 3 to 3, then AB is 1 to 2. Sorry, these are all 0 indexing, so this would be 2 2, this would be 0 1, this would be 0 2, right? This is how the pairs would be present to you already by after sorting things, because these would be compared directly and would be sorted properly, right? 1 to 1, then let's say 1 to 2. This is the sorted order that you will get. Okay, next is, with this we need to solve the main problem. Right now this is what is available to us. We know the order in which the lexicographical ordering of the strings are going to be there. Note that there can be strings which are of the same lexicographical ordering as well. Okay, these two have the same lexicographical ordering. That is also very important to understand in this one case. Okay, this is one important case. So you can kind of keep them clubbed up together as well, like these are all same, then this is different, this is different, this is different, this is different. So you can keep them clubbed up because it will be required in the DP solution. Okay, now what can we do over here? We understood the lexicographical ordering. Now we have the substrings which are there, like O of n square different substrings that are present in this particular case, in lexicographical ordering case. Okay, in the lexicographical ordering order. Now what we can do is we can go through the strings in the increasing order of their lexicographical order and then solve the problem. That is the main idea to solve this particular case, so that there is no problem of this lexicographical ordering, because if you are incrementally updating this DP of I, the previous saved DP only consists of the saved the lexicographical ordered strings that are lesser in the value. So the previous strings that you have saved as of now are going to be all smaller things or smaller lexicographical order. So that will resolve up this dependency of lexicographical ordering. So let's say you have now, I'm gonna just go over here. So you now, let's say, have an L which is ordering of, let's say, L1 to R1. This is like the ordering of the substring that is going to be there, L2 to R2, so on up till L some n square to R square, O of n square to R square, like R of n square. These are like different substrings that are present, order n square. Obviously I'm just not calculating it properly, but this is the n square different string. This is O of n square different strings that is available, already sorted by the lexicographical value. Now what we're going to do is we're going to maintain the DP of, like, what is the best thing that ends at this index. Okay, so we will first process this. Okay, so this segment ends at R1. So DP of R1 has a potential value that it can maybe take this string. So if you take this string, this is going to use the DP of what is the best that could have potentially ended. So if you take this, L1 to R1 is now blocked. So you will get the length A of R1 minus L1 plus 1, this is the length, this is the cost that you will get, plus if you take this, you're gonna need the maximum score that you can make from the previous ending points, dp of I, where I is in the range. Okay, this is the range. So if you take this particular segment, the best you can make is going to be stored over here, updated over here, like taken a max width over here. And the best you can do by taking this segment is you take this much segment, so this cost is added, and you have to take the previous string now lesser than this lexicographical ordering before this, okay, before this. So what will happen is you will take this and you will try to find what is the best lexicographical ordering string previous to this one available in the like previous indexes. That is what you loop through, which ends at a previous index than the L side of this. Okay, this is the I. What is the best that ends over here? Any possible I. Now note that for this one segment, you need to loop over all different I's, but this is O of N transition, which is fine. Okay. And this potentially updates O like a dp of Ri, which is the endpoint over here. So this is like only one position update. Okay. So for every element over here, we're gonna go ahead and do this same thing. So if I had to write it, I have to write the transition for every L comma R belonging to the segment L and R, the segments in the ordered lexicographical order. Okay. dp of R, like ending at R, is whatever we could do previously best, ending at that position, and maybe we can take this segment. So if you take this segment, dp of, not really dp, we're gonna have A of the cost that is there for this length, plus whatever best you could do, min over here, sorry, not really min, max, the maximum score that you can get across all different endpoints before the starting point of this segment, because you don't want an overlap with 0, that whatever you could build till that particular process in the end over here, dp of I. What is this? This is going to be I over here, right? So this is the best you could do. Now this is how you update a dp of R. Now note that since you're like looping in the order of increasing lexicographical ordering, the dp at the current time only contains things that are of lesser lexicographical ordering. So you will never like maybe combine something with something which is previous and has a bigger lexicographical ordering. So that's why we are using this ordering. There is one small caveat over here. You cannot really even combine things which are of the same lexicographical ordering, right? If they have the same lexicographical ordering, then you still don't want to combine things together. In that case, what you can do is you can make sure that if this is equal to this, okay, in the sorting order, when you're sorting it up, if this is equal to this in the length and in lexicographical ordering, maybe if there are two same strings, any string depends upon previous string. So make sure that this occurs before. So sort it by its lexicographical ordering. But if the two strings are same, if the lexicographical ordering is same, precisely same, then use their L to sort the things, so that I would say the one that ends first comes later. So minus of L, this is the sorting order that you will use, so that two things which are same, exact same, they don't really coincide, because in the problem it is given that increasing are strictly increasing, right? So this will handle the case of strictly increasing, that if there are two strings, let's just to understand, A, B, C, A, B, this is string over here, this string over here. If you update this string first in dp, so at this endpoint you will get one possible string, okay, and then if you update for this, you will update this length, plus you will also get this thing, but they are two same string, right? They are not strictly increasing in lexicographical order. So first update these strings, then update these strings. So go in order of L decreasing when they have same lexicographical value. So that's how you sort it, so that you don't really get a problem of this overlapping of like ordering, and so that it's strictly increasing. And once you have this, we are done. If it's not strictly increasing, then if it's non-decreasing, then you can go ahead and make it like L. This is a trick that is used to kind of implement such things. Okay. Now, once this dp is done, you can see that this is actually like updating just O of this, like for each element, it is O of N, and there are O of N square elements. So this is O of N cube dp. And finally, we can go ahead and like the answer is going to be equal to max of dp of I. like whatever ends at index I across all the things, whatever best substring chain of substrings that end over here is what we keep over here at index I. So we take the max across all of them. So that's how you can solve this particular problem, and this is going to be a O of n cube solution. Okay, you can even make this solution O of n square log n-ish by just maybe like where you have to make the max call for the previous elements over here and update the things. You can use some Fenwick tree, or like since this is from 0 to L, you can even use Fenwick tree or segment tree, and you would be able to get it into n square log n kind of complexity as well. So maybe 2000 or 1000 kind of complexity would have been also a like great constraint. But fine, I mean, for this like 2.5 hour context, even if you think this much, it should be good enough. Okay. So that's almost all the solution for this particular problem. I hope you understood the idea. If not, make sure that you go back and watch again. If you're liking the stream, definitely like the video. And let's move to the next problem. The next problem that we're going to take up is this beautiful array problem. I personally felt that this was more easier than the last problem at least. And right, so, I mean, it's actually much easier. But again, you need to make sure that you understand the constraints properly. I mean, this constraint is what makes it easy, or else this would have been much more difficult. But yeah, the problem says that you have an like 200 number given to you, and what you need to make sure is that like after swapping or changing, so you can swap elements and you can change elements to any integer, you can make sure that no two elements which are like two different, I mean one space, two space different at a distance will never be same, and ai is equal to ai plus 3. This is always true. Okay, you have to make sure that this happens. Find out the number of like minimum number of operations that you have to do. The two operations are defined like this: swap and replace. What is the minimum number of moves required to make it beautiful? Okay, that's what is the question. And it's a very, very straightforward problem actually. I don't know, like maybe the leaderboard kind of disguised it as a difficult problem, but the way it works is that if you have a1, a2, a3, so on up till an, right? What we can kind of look at is that if every third element is same, we need to make sure that this is equal to this is equal to a7, this is equal to a10, and so on, right? Similarly, a2 is equal to a5, okay? a5 is equal to a8, and so on, okay? a3 is equal to a6, a6 is equal to a9, and so on. So there is a three different chain that gets formed, and no two neighbors are same, right? No two distant neighbors are same. So a2 and a4 are not same. So this red chain cannot be equal to the blue chain, okay? And a3 and a5 is not same. So green chain cannot be equal to the red to the blue chain, and the a3 is not equal to a1. So green chain is not equal to red chain. So if you fix the first three values, they have to be all different, number one, for bigger cases, okay? And like the chains are going to have the same value. So you have to just make sure that you choose the first three values correctly, and that is going to decide the whole like array. And then you have to find out the cost to kind of convert it to that, okay? So we're going to consider the cases where things are bigger. Let's say n is bigger than 4, because there are some small caveats that happen in this problem, which is less than equal to 4, you have to handle it separately, which I felt was like pretty obvious to catch if you had seen the samples properly, okay? So which made it much more easier. Like had the samples been all bigger, I think the problem would have been much more tougher, because many people would have missed cases like 3, 4 and things like that, right? So the 4 case was already there in the sample. So what we can see over here is we can try and check how do we maybe find out the 3 different elements which is being used. So let's try to find out the cost if you use, let's say, x over here, y over here, z over here, provided x, y, z are not same, okay? So how do you find out the cost? So first of all these elements needs to be converted to x in the like 1, 4, 7 positions, y in the 2, 5, 8 positions, and a3s, a6 and a9s needs to be converted to z. So let's say for the starters, everything is different. So you convert everything, that takes you n cost, okay? But in case in the first chain, in the red chain, okay? So first chain is the red chain. In that, if there are already x's present, so the chain first, the count of the x's in the first chain, whatever that is, you don't need to convert those indexes into x, right? Because they're already x. So this doesn't need to get converted. Minus in chain 2, you don't need to convert the elements which are already y. The count of y doesn't really get changed in the chain 2. So these are the count. So C of x comma y tells you that what is the, so x can be 1, 2, 3, 1 being the chain of 1, 4, 7 and all, 2 being the chain of a2, a5, so on, the blue chain, and 3 being the chain of green, okay, green elements. So find out the y, and we also like don't want to convert anything which is gonna be let's say in the green chain with a value z. Also, how does the swap helps us, right? Let's say the red chain contains a y and the blue chain contains an x, right? If the blue chain contains a x and the red chain contains a y, maybe to swap them would be better, right? Because in one swap you will get both of them fixed together, so one more move would be saved, okay? So let's say in the red chain there are c of 1 comma the element y, whatever blue chain required y, the red chain contains this many number of y's, the red chain and the blue chain contains this many number of x, okay? So if we can swap them among each other, we will save one move, because individually both of them we need to get converted, okay? But if we swap them, we're gonna need one lesser move. So whichever is minimum, that many number of moves we can make using swaps, and that many like extra costs of converting things to a new value would be saved. So subtract the minimum of these two values. Now since x and y cannot be same, y and z cannot be same, and x and z cannot be same, we can simply exclude also min of c of 2 comma y, sorry 2 comma in the 2 whatever z's are there, and 3 comma y, okay? We can also subtract, because these are xy are different colors, they will never influence each other. So c of third chain containing the first color and c of first chain containing the third color, right? We can swap among each other then. So these are all the things that we save using swap. This is swap save, and these are like no conversion, like you convert everything but you don't convert the ones that are like already there. So it's that way. So this is the full cost, right? This is the full expression for the conversion of costs of converting the whole array into colors x, y, z, right? And you can see that these counts can be pre-computed very easily. It's a 3 cross n size array, and everything in over here you just need to plug in the value of x, y, z, and it's an order 1 formula. This is an order 1 formula, right? So what we can do is we can loop over different possible values of x, y, z. N is only up till 200. So we can do an O of n cube. Just loop over different values of x, y, z, maybe up till n plus 2. Maybe we need to introduce a new integer. So just loop till 1 to n plus 3, 1 to n plus 3. Maybe we need a new integer. So just loop into that particular space as well. Though we might not need that many, but still you can loop over all these things and it will be still O of n cube, right? And for each new color, you can simply get this particular thing computed in O of 1. That will be the cost to convert to these 3 colors. So you can just loop and just find out what is the cost to convert to that thing. And this is O of n cube solution. The constraint was pretty lenient, so we could use this particular solution, right? So that's the whole solution, in fact. One small caveat that was left in the problem was to kind of handle cases like 4, where let's say there is this first, second, third, fourth. So the interaction is this and this cannot be same, this and this cannot be same, and this has to be same. But that doesn't tell me that this and this has to be different, right? So the second and third element in this case can be same. So this is another thing that was to be handled in the thing. So n less than equal to 4 need to be handled separately. What I would have done in such cases is very, very simply, if the values are less than equal to 4, no, simply brute force 5 colors for each one of them, and find out the answer, because it would be 5 to the power 4, okay, at max, order 5 to the power 4. Just brute force that and find out the cost, okay? Brute force 5 colors for everything, and that should be enough, because, and make sure that you update the conditions. The conditions is going to be a bit different. You don't really check this with this, and for 3, like it's just that these two should not be same. That's the only condition. This can be anything over here. So for different cases you have to update the conditions, but just brute force every color that is feasible. The similar idea from the previous part. So brute force it, just make sure to handle these cases properly, because the interaction would change a bit. So that was the only caveat in the problem. Everything else was like this direct O of 1 formula and just brute forcing every color, which made the problem very simple, provided that you could see that this will be an O of 1 formula. So there are 2 small steps in this, 2 main observations. One, there is an O of 1 formula that tells us the cost. And the second thing is that you have to handle the less than equal to 4 condition very neatly. So if you could have recognized this one, this could have been solved in the contest very, very easily. Okay. So that would be all for this particular problem. Let's move to the next one. Next one is a much more interesting math problem. Okay, so we are left with two more problems. We're gonna look at the next problem, which I felt was one of the best problems of the set, and kind of one of those deciders which decide like kind of the winning teams in general. Because if you can solve such mathematical problems in an actual 2.5 hour setup, that means that you have real good capabilities to kind of get to the like world finals to a certain degree. So this is one of those problems which requires you to like sit down with maths and kind of think about how do you count things properly. And there is a lot of like kind of interesting problems that could have occurred due to the question asking for permutations. So we're going to get into that detail, but let's first quickly go through the problem. So it's like you have to pick n integers, like you are picking n integers, and it's in the range 1 to m uniformly randomly, and it's independent to each other, like every selection is independent. So what we need to do is we need to find the median of these n numbers, probability of that being an integer. That's what we need to find out. Okay, median is a collection of this. So the way it is defined is if it's an odd number, then the k plus 1 by 2 with smallest number is going to be there if it's odd, and average of k by 2 and k plus 1 k by 2 plus 1th one, average of the two middle elements in case it's even number of elements, right? That's the definition. And we have around 10 to the power 5, 10 to the power 6 kind of a constraint, which means something like linear might be required, right? Or n log n is kind of thing. Okay. So for this particular problem, the first thing that you have to definitely realize is that in case we are drawing out integers, in case k is like, if there are, let's say, odd number of elements, right, then the median is one of the picked out elements, definitely, and it's all integers. So the integer is going to be, so the like probability of that being an integer is 1. It's always an integer, right? So that's there. The main caveat happens in case of the odd even number of elements, which means you have to find out the mean, like make sure that the average of the two elements over here becomes an integer, and that's a bit difficult to compute. Okay, so maybe like I'm going to go ahead and quickly try to give you some intuition on why exactly this problem is so difficult in its true sense if you try to compute it directly. Number one is that you need to count ordered permutations, okay, or ordered draws, okay, which means like you have to make sure that the like draw that happens like 3 1 and 1 3 are counted twice. Okay, these are two different draws. You will understand why this makes it difficult later on, because you will have to kind of order the elements later on. I mean, that is one small thing. So one thing that you can try and do in such problems when you have like around 10 to the power 6 constraint, right? In general, when you see such problems, the first intuition should be that maybe I have to iterate over the median or over the like element that is causing the median. That is generally the thought process. Okay. So let's say there are even number of elements, right? Let's say there are n number of elements and the range is 1 to m. So the 1 2 3 4 5 6, let's say if n is equal to 4, then 2 3 element, these two elements are causing the median, right? So n by 2 and n by 2 plus 1th element are the one that are finding out the median essentially. So let's try to find out what will be the value of n by 2th element, and based on that, can we make it an integer, thing like that? Okay. Okay. So what we do is we first of all pick out a random elements a1, a2. We do a random draw an. Okay. Then sort it up. So it is going to be some sorted order b1, b2 up till bn. Okay. And then the middle, and then the like there is the n by 2th element. And then there is n by 2 plus 1th element, okay, in this one. The average of these two is what is giving me the median, okay, and this has to be equal to an integer. This is the problem, okay. Note that the original order is actually unsorted, or yeah, unsorted, the draw is unsorted, but we have to sort it and then find the median. So every permutation will get sorted and then we have to check the median. That is one very, very interesting thing, which is the ordered draws, which I kind of wrote over here. So in such cases, when you have to make m is integer, it's definitely like good idea to think about this part and this part separately, okay? That there are first n by 2 integers which has to be less than this side, I mean on this side of the median, and like the rest of the n by 2 plus 1 should be on this side. So there were many thoughts that even I went through when I like looked at this particular problem, maybe looping through medians and maybe looping through this element and this element. That was like the best idea which I could think of, which is generally true in such problems. So what I did was I thought about maybe looping through this particular element, and let's say this is equal to x, okay? Let's say the element which is at the n by 2th position after sorting the draws is the value x, okay? That's what is there. So what can be the values over here? what can be the values that you could potentially have over here. Okay, all the previous values before x. There are n by 2 minus 1 elements possible over here, right? What if this is x? What can be the values over here? So all these values could be anything between x to, let's say, whatever you want. I mean, x to 1, like since this is sorted in the range, they will be in the range x to 1, and they can be any element in this range, right? So the total number of ways in which you can fill, like you can create a, like after draw, let's say it is getting sorted and we are trying to form that particular string. So this is fixed to be x, we are looping over this particular value. Okay, so we are going to loop over x. The number of ways to fill these values is nothing but each of these can be in the range 1 to x. Okay, each of the elements can take a value in the range 1 to x. Okay, so it's going to be x possibilities to the power m. So there are n different positions. You place these values in different things, in different orders, but then they are not sorted, right? They are not sorted. So what we can try and do is that they are, let's say, strictly less than x. That is also a thought process that you can get into. They are strictly less than x. In that case, things like where the median is being counted like this will not get counted. Where there are multiple x's and then there are less than x element, these will not get counted. So that is also problematic. So one thing that we can try and do is maybe try to count, okay, till this much we have to end at x. So how many permutations can we create with the elements in the range 1 to x? Okay, over here, that is nothing but 1 to like x options for all the n by 2 positions. Okay, for all the n by 2 positions, minus maybe if all the positions are filled with x minus 1 values. Okay, we have this particular thing. Okay, and we need to handle one more case, which is what if they, like, whatever these choices would be there, okay, whatever the choices would be there, it will be sorted automatically. Okay, so what we are trying to do over here is we are trying to decide some like particular permutation, is some particular permutation in the original case that happened over here, x different choices for the first, like for the colors, minus if all of them are less than x. So in that case, if you subtract this, then at least one of them will be x. This is how you find this out. Okay, so this is a permuted order. Note this very, very carefully. This is a permuted order because 1, 2 and 2, 1 are equally likely in this case. Okay, and it's the permuted order in the original sequence which will get sorted to create this sequence over here. So this is the number of ways to get the permuted order in the original sequence, which will lead to a sequence ending at a value x. Okay, so this many, like this is the number of permuted orders which will finally lead when sorted into a value ending at x. Let me repeat, this is a permuted, like how many permutations exist of n by 2 elements in the range 1 to x, such that when they are sorted they will end at x. This is what we are finding. Okay, permuted values, permuted sequences. So this is what will give that. Okay, now when this particular value ends at x, how so this is one of the endpoints of the like median, right? Median is over here. It's going to be average of these two values. Okay, so what can be the potential values that you can have over here, like over here, to make it integer? Maybe that can be the value x plus 2, because if it's even, if the other part is also even, then the average of that is going to be like divisible by 2. Or in essence, the parity of these two things needs to be same, right? That's what is actually required. That whatever you did over here, whatever element you place over here, the parity needs to be same as this. If it is odd, then the other element has to be also odd. Then only it will be possible to solve it. Okay, then only the median would be an integer, because odd plus odd divided by 2 will be divisible. Okay, or else it will become a fractional. But there is a very, very difficult thing that happens if you try to compute things with placing the element over here as x plus 2 or x plus 4 or things like that. Because when you try to place it x, place an x over here and then try to find out how many sequences exist on this side and then join them together, okay, combining them back to find out the total amount of permutations that could have led to the two sides will be very, very difficult. This is what even I spent around 15 minutes of time when I was solving this problem in a notebook. That if you try to count out the same parity things, x plus 2, x plus 4, and so on this side, like these are easy to calculate. Like how many sequence ends, like starts with x plus 2, x plus 4, the same logic over here. But if you then go about, let's say, what if both of them are x and the median is also x? That is also feasible, right? In that case, since this is x, there could be bunch of x on this side too, and these x can be intra-permutate, which will not get accounted when you kind of combine these two things together, these two parts together in the actual sequence. Okay. So this is why we will do the opposite. We will count out how many times, how many different permutations exist, with this being x and the median being non-integer. Because then you will have to loop over x plus 1, x plus 3 and all the other parity thing, which is comparatively easier. Okay. And since this is already becoming difficult to understand, I'm going to explain the logic next, like when you code the things up and when we kind of understand the coding logic of this particular thing. But try to understand why the overcounting is going to happen. Because if you put an x over here, when we merge these two sides together in the original permutation, okay, it's going to be problem, because how does these x's kind of interact among each other is going to be difficult. So we will count how many permutations exist. So the problem will change, and what we will do is, there was an actual sequence over here, okay, which was A1, A2, A3. What we are doing is, we are actually finding out, let's say, actually n by 2 of the elements that are there in the original sequence are going to be less than equal to x, and x is going to be the first element in the sorted sequence. Over here, the x is the sorted part. So over here, we can get certain elements which are less than equal to x, and those would be placed over here. Okay. And then to make the median non-integer, you have to place x plus 1 or x plus 3 on this side. Okay. On this side. So it's an equivalent formula that we wrote over here, that let's say with n by 2 elements, you have to make something that ends at x. How many permutations exist that ends at that has x as the largest fixed value once sorted? That is nothing but x to the power n, the number of permutations which has x included, minus 1 to x included, minus the permutations which don't have x, so that at least one x would be there. So once you sort it up, it will contain the x at the end. Okay. This is how the number of permutation orders that can be present over here is found out. Okay. Similarly, this side we can put x plus 1, x plus 3, so that this is not an integer. So essentially, you can combine this side with any of the things that you place over here, which starts at x plus 1. So how many positions are there? Again, n by 2. How many color options you have? You had m colors over here. Sorry, m different options, numbers over here. This was x. This is x. And this can take colors or numbers in the range m minus x. Okay. In the range m minus x. And these are the values that it ends at. So the range is actually nothing but m minus x different colors, and it is going to end it over here. So what we can do is, we can try and find out that what is the start, if it starts at x plus 1, the logic would be very, very same. You have m minus x colors options. Okay. So till x plus 1, the colored options would be m minus x minus 1. Okay. That many number of colors could be possible with x plus 1 included up till m, because this side all has to be bigger, right? It's sorted. So m minus x, sorry, m minus x over here for x plus 1, obviously. All these colors are available to the power n by 2 minus, if you don't even use x plus 1 even over here as the smallest element, you would have m minus, I'm going to write it over here, m minus x minus 1 as to the power n by 2. This is what will be there. Then if you use x plus 3 over here, then the number of colors available is m minus x minus 2 whole to the power n by 2 minus m minus x minus 3 whole to the power n by 2. Okay, that is going to be over here, plus so on up till this is going to be whatever 1 0 whatever the end is, right? Whatever is the end is. So we can compute these values separately. So these are independent, based on every x you have a certain ending point over here, right? Every x, m is fixed, x is dependent, x is variable, right? So for every different x, we can compute this expression, and we can add a new value in the front. If you add m minus x plus 2 minus m minus x plus 1, this will create the next answer for the next term that would be required. So we can incrementally build this one using a DP if you have to do it, but also you can use a, let's say, some sort of like power summation if you have to do it. But in general, this would be better to do it with a DP, because at the start, what we need to do is essentially we will keep a DP of I, which will tell us, okay, DP of X, which will tell us you can place the colors. So there are n by 2 positions, and you can place colors you have to start at X or X plus 2 or X plus 4, so on. This is what the DP of X will mean. You can simply calculate this DP very easily using this formula, that DP of X will tell you will be equal to, you can use X color over here, which is M minus X, the same thing that we wrote over here, this term over here. M minus X whole to the power n by 2 minus M minus X minus 1 whole to the power n by 2. If you don't use X, then it will not be possible. Sorry, this was X plus 1, right? We are using X plus 1 over here. I mean, anyways, we need to find out for X plus 1. So I'm just writing DP of X plus 1, just change the definition. You can do that. I mean, if you're solving this problem, I'm assuming that you are already good at basic DPs and calculating such functions in an incremental DP, most probably. So this is there, and next we like plus, if this is done, then we can potentially use X plus 3. So we will use DP of X plus 2. This is how we will kind of calculate the formula. I mean, since I've written it X, let's write the formula with X only. So if you have to start at X, you have to do this. You have this much of color possible minus M minus X whole to the power n. That's the formula for this, plus DP of X plus. So this is a DP that you will have to calculate for every index. Okay. And then for a certain, so this DP gets calculated with a mathematical formula simply. And then this is the number of different colors that end at either X plus 1 or X plus 3. So what you will do is you will use this formula to find the number of permutations that end at X. Okay. And then you will find out the permutations that will start at X plus 2 or X plus 3, so on. Using this, all thing would be computed by DP of X plus 1. Okay. So this multiplied by DP of X plus 1 will give you the total amount of permutations that are feasible. And then you have to divide by M to the power n to kind of get the probability, and you have to combine them back into the original permutation. So now let's go back to the final thing, the final step. Okay. So what we did was we had the original sequence, okay, which is unsorted. Okay. So the way we are doing it is we will choose which positions are going to be in the left half and on the right half to count things. So let's say n choose n by 2 are going to be the positions which are on the left half. Okay. I'm going to write over here, are on the left half. If it's on the left half, let's say we are counting the number of permutations which are like giving us an odd endpoint or odd median. So we are just going to sum it up across all different X. After sorting it up, the one side endpoint is X, other side can be anything. Okay. So to end at a color X after sorting for all those colors which are less than X. So we have n by 2 values which are chosen, which are less than X, and we will copy this sorted thing into this particular thing in an ordered way. Okay. So we choose the ordered sequence which will end at X after sorting. That is nothing but X to the power M. So sorry, not really M. You have 1 to X as an option over here. So you have X different colors as an option for n by 2 positions, minus, in case X is not present, then that will not be valid. So you subtract all those cases, X minus 1 whole to the power n by 2. Okay. This is the number of permutations that will end at X over here after sorting, after choosing the positions and like placing numbers on those things. This is the placement on these positions. Okay. And it will get sorted and it will end at X, multiplied by DP of X plus 1, because this can have X plus 1 or X plus 3, so on up till anything which will compute this similar kind of thing, so that it doesn't really have the answer being calculated as the final answer. And this is up till M, obviously. This is going to be like the DP for all the ones that are going to give us an odd or different parity number, and median will not be non-integer. So this is the total amount of sequence that will give us non-integer thing. You can maybe find out the probability by dividing this by M to the power n. like, because that's the total number of colorings that we can get for the whole original sequence. So note that this is very interesting. We are doing over here for the original sequence, and then it's getting sorted and being placed at X. So that's where ordered and unordered kind of comes into picture. I understand that this is a bit of maths heavy, but that's what you will have to understand. Okay, so this is what we will use for this one. And this is like for this probability of the sequence being having a midpoint as the non-integer. Simply subtract 1 from out of it, and that's going to give us the full formula. So this is the full formula to solve this particular problem. Okay, so we are choosing the places where things are less than the median, and we are placing this value. This can take anything in the range 1 to x. This can take anything in the range 1 to x. So we place the values first over here, then bring it over here and get it sorted and ensure that it ends at x. That is the amount of ways in which you can keep things in these original places. Okay, make sure that you have to add this n choose n by 2, because you have to choose first which positions are going to be on this half and this half, okay, in the original permuted sequence. And then the rest of the parts which don't give us an integer is this one, and you like subtract it off. I personally first went into this direction, that this we will try to compute where it is an integer so that I don't have to subtract, but it is incrementally very, very difficult. But if this is x, then some of these will also contain x, and then you have to compute the intra permutations between this x's and the lesser x's and the bigger x's, which is not possible, at least at this complexity. Okay, so definitely this is the final formula, and this is how you can solve this particular problem. Okay, so that's all about this particular one. I hope this is like one heavy maths problem, but I hope you've understood some of the parts. Try to not write these things down in the notebook and try to solve this one. This actually is the differentiator problem, so I think most of the hard people, folks who solved the harder problems, would be able to solve this one. So if you're absolutely new, or if you're in the intermediate stage, maybe you can skip this problem for now, but if you're really interested in maths, definitely solve this one. Okay, so that's there. Now we are left with one more problem. If you enjoyed this particular stream till now, or this video till now, definitely like the video and subscribe to the channel. We will have more such videos, more such interesting problems from different places onto this channel. And make sure to share this particular video with more folks who have participated in ICPC, maybe your teammates, maybe your juniors, who would be interested to kind of learn the ideas for these particular problems. Okay, and next we're going to move to the last problem, which is fairly difficult. So I'm going to go through the idea in a light way, but I will expect that you guys can maybe read about it from there. Okay, so let's move into the last problem. Okay, so let's move to the last problem, which is tree regression. Now, this particular part is not going to be a full editorial of this, because I feel this is a fairly hard problem and doesn't really makes sense to explain it in a very elaborate way. Maybe some editorial gets uploaded on this one, and that would be better. But I'm gonna just give you the ideas, and most probably in this video from now on, I'm assuming that I'm addressing to someone who has been doing competitive programming for some time now and kind of understands tree queries and stuff like that. And if you are absolutely new, maybe the next section is not for you, so you can drop it off, but definitely check out the other videos on the channel. You will enjoy that. But now let's kind of get into this problem and understand how to solve such things. So I'm assuming that you're already a good coder. So for this particular part, the question is that you are given that for a particular two pair, we have the distance as the distance between the two. For a path to a node, it's the shortest path, the closest node distance from the node. Okay. For a set of nodes to a path, you have to find out the maximum. So the node that has the maximum distance from the path is the one that you have to find out. Okay, and that is the max that is being used over here. And what we need to do is that for a given set of nodes, we can choose over any particular path such that the maximum distant node in the set is least distant. Okay, the question is, for a set of nodes, so in a tree given to us, for a set of nodes, okay, set of nodes maybe, okay, choose a path such that the most distant node in the collection that is given to you, the marked nodes, is least distant. That is the question. Okay, so in this case, maybe we can try and pick this particular path so that the most distant node from this path is either this or this, which is least in total sense, which is at one distance. Okay, this is also at one distance. If you had taken any other path, like let's say on this, so this would have been at a 2 distance from this particular path, right? So we have to find out, for a set of nodes, find out a path, or find what is the optimal path that leads to the farthest node from this path be at the closest point, be at the closest distance. Okay, that's the question. So for this, like as soon as you see the problem, it should strike in your mind that this is actually an auxiliary problem. There are fairly good amount of intuitions or like hints in the problem that the sum of nodes are like less only, and for a set of nodes, like there are only fairly good amount of ideas, right? When you have tree queries in a problem, that if you have, let's say, so being square root kind of removed off from the picture, square root can be applicable on almost every idea. But if you have, let's say, path queries, you use HLD, right? When you have subtree queries, you use Euler 2, right? Euler 2, or maybe some other techniques as well, but generally this is the case. When you have, let's say, updates and queries based on paths or maybe subtrees, you can use something like centroid, right? When you're given a set of nodes and you have to compute something with respect to that set, generally it's auxiliary tree, right? Maybe dominated tree is another thing which can be helpful, where like we need to depend upon like every path flows through a node. If this is the terminology being used at such problem, maybe dominated tree is something which can be come into picture, right? Dominator tree. Then reachability tree can be another thing which can be used in a problem. Like let's say the paths are being in an incremental way, then reachability tree can be another thing that can be used. I don't think like we need anything more than this, right? And if the tree query contains everything, maybe a linker tree can be the thing that we use, right? So that's almost all the ideas that we generally exist for a harder problem of tree. I mean, query problem of tree. And for simpler problems, you have binary lifting, which can solve most of the problems, right? Without any updates. That's again a very, very interesting idea. Like DP plus binary lifting is a very common terminology that is used to solve most problems. Then HLD, Euler 2, linker tree, reachability tree, dominated tree, auxiliary tree. So when you're seeing a tree query problem, most probably it's one of them. And as soon as you see that there is a set given to you, you should link it to auxiliary tree itself, because the path is like a dependent thing on auxiliary tree. Now, I'm not going to make a for this video a full detailed video of auxiliary tree because it's a complicated topic. But I think there is a video by you can Google it up. I think there is one video. You can check it real quick. It is already up, like there is a video which explains the idea. There is a good blog as well which you can read if you just Google it up. So you can read about auxiliary tree. The idea is very, very simple. The idea is essentially this: like if you have a tree like this, let's say, okay, let's kind of get into this. If you have something like this tree, and then you select a bunch of nodes, okay, let's say this, okay. So what auxiliary tree kind of creates is it creates a tree which is going to contain a bunch of nodes which are potentially some LCAs of any two pair, okay. And the way to create that is like there is a possibility of linearly creating it using stack and like just going through the Euler order, the in time order of the nodes. And what we can do is we can kind of get through this node. You can compute this node, like LC of this node and this node, so which gives you this node. LCA of these two things kind of gonna give you these two things are gonna give you this. So the final like tree that gets converted over here is going to be, this is going to be present in the final node, okay. Then this node is present. This will be short circuited directly into this node, and you will get the interesting like the nodes over here. And then this should be short circuited as well, and you will get the two nodes over here, okay. So this will be merged into this particular one. I mean, it depends like how you want to do it, but ideally this is how it's done. Like this is what is being done in this case. So this is going to get merged into, these all things are going to be merged into this one. So that's how auxiliary tree works. And what it essentially creates is like a bunch of trees, nodes which are like kind of relevant and like compressed together in components, right? So now what makes it easy to kind of solve with this one is, now it's a standard problem of DP on tree now, wherein we have to solve, let's say, how do we find out the best path that leads to the minimal weight of all the nodes, okay. So in this case, if you have n nodes in the query for the set, when you create the auxiliary tree, it kind of goes ahead and it contains two, like if it contains n nodes in the query, it contains 2n plus 1 number of nodes in the auxiliary tree at max. That's how it is there. So for every query, you can create this new tree, which is going to be order like this number of s in the query complexity, and then you can do a like a tree DP kind of thing, which is order like s, that can solve the problem, so that every query can be done in a summation way, so that finally the query complexity doesn't really exceed O of n or n log n. Obviously you have to build lifting and stuff to process things up, but this is how you do it. Now once you have a tree, and you in this particular tree you need to solve the problem that find out a path such that, like, we can now use linear complexity to kind of process the thing. But what the question is now, you in this particular tree you have to find a path such that the sum of, let's say there's some more nodes over here as well, it doesn't really need to be like this, the sum of distances, sorry, the most distant node from that path is least. Okay, that's what is, let's say, asked. I'm going to add one more node over here. Okay, so the way we do that is a standard 3DP problem. It's an in-out DP kind of a setup. So let's say we are considering this particular node. So there can be a bunch of types of path that goes over here. Maybe one path goes up and somewhere else, right, on this side. So it's an out DP, and one of the path goes inside, something like this. So in that case, the best, so if you don't let a path go this side, or if the path goes this side, we can calculate, okay, this is going to be the, like, in this side, what is the most distant, like, interesting node. So that would be at distance 3, and on this side you can find out that it's at distance 1. So you will definitely try to go to the one that has, like, most distant one over there, because that will reduce it and this will be lesser. Because anyways, if you go on this side, the answer is 3. So maybe better try this side and then go with 1, or you will anyways take min with all of them, so it doesn't really matter. And the way we do that is we go across. So there is obviously, like, in problems on these things, like, what is the cost if you get a node. So simply calculate this way: dp of node comma, like, is the path coming right now to this node, yes or no? If that is the case, then it will continue. Okay, or if not, maybe you can try finding it out. So if is a path coming over here. And another thing that you can try and maintain, like, just I'm gonna just show you guys exactly. So the way we maintain this kind of DP is path started, and it's in some other subtree, it's in some other node, okay, some other part of the tree, or it's going to be the path is coming over here to this node, like it's coming to this particular node, or it might be that the path will start over here. So path will start over here. That's so path not started. So this is the 3 different things that you can kind of process over here, and the different ways in which you can kind of handle that is, like, for this node, if the path is somewhere over here, then the in DP over here is gonna, like, process how much distant is some node over here in this side, and that will give me the most distant, like, interesting node on this side. So that will be the in part of this thing, in DP of this, the deep in DP part of the things. Okay, and if the path is, like, kind of going inside this node, I'm obviously, like, jumping through many things over here, but I'm assuming that I'm like kind of talking to somebody who is already, like, who knows auxiliary tree and things like that. So if you know that it's kind of coming in over here, so you know that one of the endpoints is going to go in. So you need to find out, like, what is the most distant on this part, what is the most distant node in this part, what is the most distant node in this part, and you will definitely go into this part which has the most distant one. So the second most distant, like, node is going to be the one that influences the current distant in this node, and then obviously you have to do the subtree part for this one. Okay, and like, the third thing that you need to do is, if, like, you have not started, then maybe in this case you have 3 different childs. Okay, 3-4 different childs. Maybe what happens is that there is going to be a path which starts somewhere over here, it goes to this node and goes inside this, right? So what we can do is we can try to find out, like, if the path goes like this, one of these subtrees will, like, contain the, like, this is, let's say, the first distant node, like, which is the subtree which contains the most distant node. This is the weight 3, which is going to second distant node, third distant node, and this is going to be the second distant node. So it's generally optimal to go into the 2 paths that is going to contain the current distant node, and find out the W3 is what is going to get added as a cost over here at this node. And one more possibility is that there is some other node in the parent side which is at a distance somewhere over here, and you can kind of use, like, an out DP to kind of compute that what is the farthest interesting node outside on this subtree. That will give you the out DP part things to this one. So that's, like, if the path starts over here, or if the path has not started, you can even let it start in some one of the subtrees. So that's also another way which you can solve it. So that's how you can kind of process this thing. But the main idea is to kind of go through the auxiliary tree formation, so that for this query the size of the tree is very small, and then you can use tree DP. And for tree DP, it's going to require you to kind of maintain, the main idea is to maintain the 3 best, and then try to see how the path starts on which one it goes into, and the other is going to get into merged into that one. So till the third best path you need to maintain in the code, and then you will have to merge it with the best one. That's how to solve this particular problem. I think this is obviously not a full editorial. Maybe in some future days I will make a full editorial of this video with explaining auxiliary tree as well. But for now, I'm like kind of addressing the person who is like who has already solved 6 problems, and maybe also knows a lot of tree codes. They can read about auxiliary tree, and with this idea, I think they would be able to build up a solution on this one. So that's almost all the problems on the preliminary round, and kudos to everyone who has made well. Best of luck for like all of you guys to kind of qualify to the regional, so that you guys can participate in that, and then obviously to the winners, definitely have a best luck for like kind of getting to world finals. So that will be all from my side in this video. See you in the next one, where we might learn something new, something interesting. And definitely subscribe to the channel if you are new, and like the video, and comment down below if you want to learn some new technique. Suggest me if you want me to make more such things. This is Vivek signing off. Bye bye.